Okay, during class today, it seems that my students gradually disappeared. Maybe because they already know this, maybe because there's something wrong with my delivery. Uh, but we've been having some problems with Zoom, so maybe Zoom just kind of eliminated people on me. And I should probably check my email, but I'll get to that. Okay, so we started with this function here in green. And for the moment, ignore anything that's written in purple, because what's written in purple came after what we've written in green. We modified the numbers. So you see here we have -1, 2, and 3, indicating that this graph goes through the x-axis at -1, 2, and 3. Later, we modified it, and I asked the group to work it out themselves, but using -3 instead of the -1, 7 instead of the 2, 11 instead of the 3. Just an explanation of why the purple stuff is there, why the purple numbers are here. Now, the numbers that we started with were again the -1, 2, and 3 on this polynomial, and y was equal to -20. I didn't have that 1 inserted there, okay, so y is -20. With that information, we write down what this polynomial could be, at least in one form. And the polynomial could be then some multiple of x plus 1, because you need a factor x plus 1 in order to make the polynomial 0 when x is -1. If x is -1, you're going to get a 0 here. That's going to make the graph go through 0. And similarly, when x is 2, you want a 0, so you have the factor x minus 2. And when x is 3, you have a 0, so you have the factor x minus 3. You also have a number out here, because if you just do x plus 1 times x minus 2 times x minus 3, if you plug in 0, you get 0 plus 1, 0 minus 2, 0 minus 3, that's 6. Okay? The y-intercept here is -20. Not 6, it's -20. So, we have to have this number as a multiplier, so the result comes out -20 when x is 0. So we do this algebraically. We say, okay, here's our general form of a polynomial with zeros at -1, 2, and 3. Y equals -20 when x equals 0 in this case. So we plug x equals 0 in here, and we're going to solve for a. It's very simple now. If y is -20, then you have -20, which is your p of 0, incidentally. -20 is p of 0, and that's a times 0 plus 1, 0 minus 2, 0 minus 3. So that -20 equals a times 6. Well, you can easily solve that. Divide both sides by 6. You get a equals -20 over 6, which is -10/3. So your p of x is -10/3 times, again, your x plus 1, x minus 2, x minus 3. Okay, now we have a rational function. Graph of a rational function. There's an error in this graph, the way I drew it. I drew the asymptote too high. Well, the asymptote isn't going to be higher than the y-intercept, so I was a little careless when I drew the thing. Okay, and again, ignoring the purple, we see that we have a vertical asymptote at x minus 1 and a vertical asymptote at x equals 2, meaning that the denominator of your rational function is going to have to approach 0 when x approaches -1 or when x approaches 2. Because when the denominator approaches 0 and the numerator doesn't, your quotient gets very big. A concept that people have a lot of trouble grasping, even though we spend time on it. So anyhow, the y-intercept is going to be 0, 2. And you're going to have zeros at x equals -3 and x equals 5. Okay, well, zeros at x equals -3 and x equals 5 mean that we better use x plus 3 and x minus 5 for a numerator, because those factors give us 0 when x is either -3 or 5. And that's going to be the numerator, because of course when the numerator of a rational function is 0, the value of the rational function is 0. The denominator, again, has to approach 0 as x approaches either -1 or 2. So we're going to have to use x plus 1 and x minus 2 as factors for the denominator. This gives us a rational function r of x equals some multiple of x plus 3 times x minus 5 over x plus 1 times x minus 2. This numerator divided by this denominator. Again, just looking at this, if x is equal to -3, your numerator is going to be 0, the whole thing is going to be 0. If x is equal to 5, x minus 5 is going to be 0, makes the whole thing 0. If x is close to -1, x plus 1 is close to 0. And the numerator isn't close to 0. So as x gets closer and closer to -1, the denominator gets tinier and tinier, and the numerator stays about the same if you're real close to 0. If x is real close to -1, so that you have a very tiny number into a very big number, giving you a very tiny number into a number that isn't tiny, giving you a huge quotient. Maybe positive, maybe negative, but huge. Same thing as x approaches 2. Okay, so there's our function. The only thing we don't know is the value of a, but we can determine that since we know the y-intercept to be 0, 2. And this tells us that r of 0 is 2. The value of your function at 0 is 2, so that a times what you get when you plug zeros in for x's here, and that's what you have here, I'm not going to read it to you, equals 2. And we then do the arithmetic. 3 times -5 is -15, 1 times -2 is -2, so we have 15 halves. A times 15 halves is 2, so a is 2/15 of 2, 4/15. So r of x is 4/15 of x plus 3 times x minus 5 over x plus 1 times x minus 2. Now, I asked the class to solve the problem if I change the -1 to -3, the 2 to 7, the 3 to 11, and the y-intercept to -120. Well, here's the solution. Don't look at it. Work it out yourself, and then check the solution that I've written here. And let me know if I happen to do something wrong. Over here, same thing. I've changed the -3 to -5, the 5 to 7, -1 to -2, the 3 to 2 to 3, and the 0, 2 intercept to 0, 4. So how does that change everything? Well, again, here is the function, and here is the condition that the function of 0 equals 4, but work it out yourself. Then, well, yeah, okay, then I worked it out. So the board was behind that. But then here it is, worked out. But as I say, work it out yourself before you look at the solutions in purple. Okay, there it is.